quantum is real, but most quantum advantage claims die when tested, not because quantum is fake, but because reality is the strictest judge in science. Today, we put quantum computers on trial, and the verdict is complicated. In this episode, I'll give you 3 things, no fluff. What quantum advantage actually means, and why people argue about the words. The most famous advantage moment, then the brutal cross-examination that followed. The real reason advantage is hard to prove: verification, noise, and moving goalposts. And yes, there will be humor, because nothing says future of computing like a computer that must be kept colder than outer space. First problem: the battlefield starts with vocabulary. The term quantum supremacy is widely credited to John Preskill, coined in 2012, per IBM's explanation of the term's origin. It generally means a quantum computer does something no classical computer can do in any feasible time, whether or not the task is useful. But the world didn't love the word supremacy for obvious reasons, and the field also wanted a more practical target. So people started leaning on quantum advantage, outperforming classical computers on tasks that matter, or at least inch toward usefulness. So already, we have a problem. If we can't agree on the definition, we can't agree on the trophy. That's like arguing you won a boxing match because you landed more vibes. In 2019, Google announced a landmark result using its superconducting quantum processor Sycamore. In their Nature paper, they reported that the processor sampled outputs of a random quantum circuit in about 200 seconds, and estimated a state-of-the-art classical supercomputer would take around 10,000 years for the equivalent task. The world heard. Quantum computers just beat classical computers. But the courtroom doors swung open immediately. Enter IBM, standing up like the rival attorney in a thriller. IBM argued the classical side wasn't finished speaking, that with smarter classical simulation and better use of memory hierarchies, the task could be far faster than 10,000 years. And the debate spilled everywhere, because this is the weird part of quantum advantage. Sometimes the quantum machine doesn't get worse. The classical algorithms get better. So your victory can shrink after the parade. That's not cheating. That's science. Here's the nightmare. A quantum computer claims it did something beyond classical reach. But how do you verify it without doing the same computation classically? This is a core tension in sampling-style demonstrations. You're not solving a normal problem like factor this number. You're producing samples from a distribution, and verification can require heavy classical work. So a lot of early advantage claims are like, I swear I did the impossible. Cool. Show me the receipt. The receipt is also impossible. That's why the field cares intensely about verifiable beyond classical tasks, because otherwise, your claim floats in a fog of trust. Quantum systems are unbelievably sensitive. Heat, vibration, stray fields, anything, can corrupt the computation. That means today's machines often have to fight an enemy called error at every step. And this is why many researchers emphasize that practical advantage likely needs quantum error correction, where many physical quits encode one more stable logical quit. Translation: a useful quantum computer is not just more quits. It's more reliable quits, which often means many quits just to protect one, which is beautiful and painful, like hiring 20 bodyguards to escort one celebrity quit to the stage. This is the part that humiliates headlines. In 2022, Science ran a piece describing how researchers improved classical methods for simulating the kind of sampling problem used in the 2019 experiment, shrinking the claimed gap. This doesn't mean quantum is fake. It means your hard problem must remain hard against the best classical algorithms, not against yesterday's best. So proving advantage is like winning a race where your opponent is allowed to evolve mid-race. In 2022, a photonic processor called Xanadu's Borealis was reported in Nature as showing quantum computational advantage in a specialized sampling task. Even that paper explicitly notes the ecosystem problem. Earlier photonic demonstrations were vulnerable to spoofing, where clever classical heuristics can fake-looking samples. Meaning, every time quantum says beat that, classical replies, bet. More recently, D-Wave has made high-profile claims of quantum supremacy or advantage on materials-related simulation tasks, reported widely in the business tech press, while critics argue classical methods may match it, making the supremacy label contested. This pattern is the theme of our story. Quantum advantage claims don't just get published. They get challenged. Because the advantage isn't a vibe. It's a measurement. If you want a quantum advantage claim that survives the courtroom, it needs at least 4 things. A clear task definition, not it feels faster, but measurable inputs or outputs. A fair classical baseline, best known algorithms, best realistic hardware. Verification strategy, how others can independently confirm. Noise control or error correction path, how the result scales without collapsing. And this is why advantage is hard to prove. It's not one mountain. It's 4 mountains stacked in a trench coat pretending to be one mountain. So here's the twist. Quantum advantage is hard to prove because it is not just physics. It is physics plus engineering plus computer science plus skepticism. And skepticism is not the enemy. Skepticism is the quality control of reality. Quantum is real. But most claims die when tested, because the test is the point. And when a claim finally doesn't die, when it survives the best classical attacks, survives verification, survives noise, that's not a headline. That's a new era. Comment courtroom if you want the next episode. The day Google claimed quantum supremacy, and the exact reason IBM said not so fast. Subscribe, because on this channel, we don't just chase strange tech. We put it on trial.